Now see here, this is a Carnot cycle or Carnot engine. Actually this is an ideal engine which was designed by Carnot, and its working is completed in the 4 steps. So now we have to discuss the working of an ideal engine designed by Carnot. That is why it is known as Carnot engine or Carnot cycle. Now see here, in this one there is a first part of this engine, that is source. Source has got temperature T1. Whatever the heat is taken from the source, its temperature remains same. It means it has got infinite thermal capacity. Now this is the insulating pad, completely insulator. There is a cylinder whose walls are here perfectly non-conducting, but the bottom portion, this one is here perfectly conducting, and this is fitted with a piston, frictionless piston, and inside it, this cylinder, an ideal gas is taken, and this ideal gas is taken as working substance. Now there is a sink in which heat has to be given or released. Whatever the amount of heat is given to this, its temperature remains same. So we can say it has also got infinite thermal capacity. And now T1 and T2, T1 is greater than T2. So now see here how does its working here completed and completed. That means all the steps of the working, first one by one. First one, this cylinder is placed over this source. This portion is conducting and this part of the source is also conducting. When the cylinder is placed on the source and gas is allowed to expand isothermally. So initially its parameter are, I am showing this one with the help of the graph. Initially when this cylinder is placed over here, its initial parameters V1, volume is V1, pressure is P1 and temperature is T1. Now the gas is allowed to expand isothermally, so temperature remains constant and gas expands until the temperature becomes V2 and pressure P2. So this is the graph AB for the isothermal expansion. This is the first step of the working of Carnot engine. Now this cylinder is taken out from here and placed on the insulating pad. In that case, again gas is allowed to expand, but this expansion is adiabatic expansion because there is no supply of heat. So when this gas expand now here, so initially temperature was T1, now its temperature changes to T2 and volume changes from V2 to V3 and pressure changes P2 to P3. Now this cylinder is placed on the sink and this gas is compressed, and it is compressed such that it is compressed isothermally and it is compressed such that its volume becomes from V3 to V4 and pressure is P3 to P4 and temperature remains same T2. And when it is placed here, so during compression whatever the heat is produced, that is going to the sink. So heat released is going to the sink. So this is called isothermal compression. So here the work is done on the system, work is done on the gas, and in the first two steps work is being done by the gas here. Now in the last step, again the cylinder is taken out from here and placed on the insulating pad, and the gas is compressed, but this compression is adiabatically. It is compressed such that its volume reduces from V4 to V1 and pressure P4 to P1. And in this adiabatic compression, pressure temperature from T2 to T1, it means the working substance has returned to its initial state. So one cycle of the working has completed in this way. So there are the 4 steps. First from A to B, that is isothermal expansion, then B to C, that is adiabatic expansion, C to D, that is isothermal compression, and D to A, that is adiabatic compression. Now just we have seen working of the Carnot engine. Now just we will write the expressions for the work done in each steps. First one is, I will write here, that is isothermal expansion. In isothermal expansion, cylinder is placed on source and heat absorbed is, that is suppose Q1. So we can write here Q1 is equal to RT1 log E, that is V2 upon V1. In the diagram you can see, and if you calculate graphically by the area, so whatever the area is enclosed here with the graph AB and this volume axis, that complete area is equal to work done. So, this is the formula for the in first case. So, whatever the work done is here in this case, that is equal to heat absorbed, because there is no change in internal energy. Now, in the second step, that is here from B to C, that is the adiabatic expansion. So, we can write here in adiabatic expansion, in this case temperature is changing from T1 to T2, volume is V2 to V3 and pressure P2 to P3. So, we can write here the work done is equal to here, this one you can write W1 and this we can write W2 is equal to here R T2 minus T1 divided by 1 minus gamma. Already we have calculated these we have done these derivation earlier. Now, in the third case, when C to D compression is taking place, in that case we can write here. So, third one is isothermal compression. In isothermal compression, the work is done on the system. So, the work done is taken negative. So, we can write W3 is equal to minus RT2 log E V4 upon V3. In that case, we can write here minus, so we can write here RT2 log E V3 upon V4. So, this is the work done in the third case, and this work done will be equal to heat released or heat given to the sink, that will be here Q2. So, work done W3 is equal to Q2. Now, the fourth step of this working is here, that is adiabatic compression. In this case, cylinder is placed on insulating pad and the gas is compressed so that it retains its initial state. So, in that case the work done on the gas, that is W4 is equal to, we can write, since work is done on the system here, that is from V4 to V1. So, we can write here minus R here T1 minus T2 upon 1 minus gamma, and we can write here R T2 minus T1 upon 1 minus gamma. So, we have written expression for work done in all the 4 steps. So, the net work done we can write W is equal to W1 plus W2 minus W3 minus W4. But see here, W2 and W4 are equal. So, these two will get cancelled here. You will be getting net work done is equal to W1 minus W3, and that you will be getting here Q1 minus Q2. So, the net work done in one cycle is equal to here Q1 minus Q2. So, now we can calculate efficiency of this engine.